Picture this: a world untethered from any star, drifting endlessly through the cold, silent void of space. No sunrise, no sunset, just perpetual darkness stretching in every direction. This isn't science fiction. It's the reality of rogue planets, cosmic nomads flung from their birthplaces and left to wander the galaxy alone. But here's the twist: these forgotten worlds might not be as barren as they seem. Hidden beneath icy surfaces or within vast subterranean oceans, life could be clinging to existence in ways we've barely begun to imagine. What if the key to finding extraterrestrial life isn't on a distant exoplanet orbiting a star, but on one of these lonely, starless wanderers? The universe is full of mysteries, but rogue planets are among the most haunting. Imagine a place where the sky isn't just black, it's empty. No familiar constellations, no distant suns, just an unbroken expanse of nothingness. These worlds were once part of solar systems, but gravitational chaos ejected them, sending them spinning into the void. And yet, against all odds, some might still harbor the ingredients for life. Deep beneath frozen crusts, geothermal heat could melt water into vast underground seas. Chemical reactions might brew the building blocks of biology in total isolation. If life can thrive in the crushing depths of Earth's oceans or the toxic vents of volcanoes, why not on a rogue planet, where the very darkness could be its shield? This is where the story gets even more fascinating. Scientists once thought these planets were barren wastelands, but now they're asking a daring question: could rogue planets be galactic arcs, carrying life from one star system to another? If even a single one of these nomad worlds shelters microbes, or something far stranger, it could rewrite our understanding of life's resilience. The hunt is already on, with telescopes scanning the darkness for hints of warmth, chemical signatures, or even faint whispers of atmosphere. Every discovery pulls us deeper into the mystery, so buckle up, we're about to explore the most alien ecosystems imaginable, places where the rules of life, as we know them, might not apply. The universe is stranger and more wondrous than we ever dared to dream. Rogue planets are the universe's ultimate drifters, celestial orphans, untethered from the gravitational pull of any star. Unlike the Earth, which basks in the warmth of our sun, or distant exoplanets locked in orderly orbits around their own stars, these wanderers move through the galaxy alone, untethered and unseen. Some were likely born in the chaos of young solar systems, violently ejected by gravitational tug-of-wars between larger planets. Others may have formed in the cold, dark spaces between stars, collapsing directly from rogue clouds of gas and dust without ever knowing the light of a sun. What makes them so intriguing is their invisibility. Most planets are discovered by the way they dim their host star's light or tug it slightly as they orbit. But rogue planets emit no light of their own, and with no star to betray their presence, they slip through the cosmos like ghosts. Only in recent years, thanks to techniques like gravitational microlensing, where their mass briefly bends the light of distant stars, have we begun to uncover their existence. Even then, each detection feels like catching a shadow in the dark. Their origins tell a story of cosmic upheaval. Imagine a young planetary system, unstable and violent, where giant worlds like Jupiter hurl smaller neighbors into the void. A single close encounter can fling a planet clear out of its star's grasp, sending it spinning into the interstellar abyss. Yet some rogue planets might never have had a star to begin with. In the deepest reaches of space, pockets of gas too sparse to form full-fledged solar systems could still collapse under their own gravity, creating solitary worlds born into eternal night. the mystery doesn't end there. Without a sun to warm them, these planets should be frozen wastelands, but nature has a way of surprising us. Tidal forces from orbiting moons, radioactive decay in their cores, or even thick insulating atmospheres could trap enough heat to keep underground oceans liquid. If life can thrive near scalding hydrothermal vents at the bottom of Earth's oceans, who's to say it couldn't cling to existence in the depths of a rogue plan, its hidden seas? These lonely worlds might be more than just cosmic curiosities. They could be the ultimate survivors, carrying the potential for life through the galaxy's coldest, emptiest stretches. And if that's true, the universe might be far more alive and far stranger than we ever imagined. Finding rogue planets is like trying to spot a single black marble rolling across an endless black floor, nearly impossible with conventional methods. Without starlight to illuminate them or predictable orbits to track, these dark wanderers force astronomers to get creative, the most successful technique so far. Gravitational microlensing. Here's how it works. When a rogue planet drifts perfectly between Earth and a distant star, its gravity acts like a lens, bending and magnifying the star's light for a fleeting moment. That tiny flash, lasting hours or days, is our only clue to the planet's presence. It's cosmic detective work at its finest, catching shadows in the void. But microlensing has its limits. The alignment has to be flawless, the timing impeccable, and even then, we only get a snapshot of the planet's mass and rough distance. That's where infrared telescopes come in. While rogue planets don't reflect sunlight, they do emit faint heat radiation, especially younger ones still cooling from their formation. Instruments like the James Webb Space Telescope are designed to pick up these whispers of warmth, scanning the darkness for the thermal glow of a world untethered from any star. Then there's the indirect approach, watching for gravitational disturbances. Just as a ship leaves ripples in water, a rogue plan, its mass, can subtly distort the motion of nearby star clusters or gas clouds. These minute wobbles, detectable through painstaking observations, hint at an invisible culprit lurking in the darkness. Still, it's like hearing footsteps in an empty room. You know something's there, but you can't see it. What makes these worlds so hard to pin down isn't just their stealth, it's their sheer isolation. Most exoplanets are found by studying their host stars, but rogue planets have no such anchors. Every detection is a triumph of patience and ingenuity, a reminder that the universe hides its greatest secrets in plain sight, if only we know how to look. And with each new discovery, we're rewriting the rules of where and how planets can exist. The hunt for these cosmic phantoms is far from over, but one thing's certain: every shadow we unmask brings us closer to understanding the true diversity of our galaxy. Drifting through the interstellar void, a rogue planet carries the silence of eternity. There's no dawn to break the endless night, no seasons to mark the passage of time, just an infinite expanse of darkness, colder than the deepest reaches of Antarctica. Temperatures hover near absolute zero, the kind of cold that would freeze air solid if there were any to freeze. Without a star to warm its surface, the planet's outermost layers become a barren wasteland of ice and rock, untouched by warmth for billions of years. Yet even here, in this frozen purgatory, the planet isn't entirely still. It moves slowly but irresistibly, pulled by the faint tug of distant galaxies, a wanderer with no destination. Imagine the solitude of such a journey. While other worlds dance in orderly orbits around their stars, this one sails through the emptiness alone, unmoored from the rhythms of a solar system. Its path isn't straight occasionally. The gravity of a passing star might nudge it slightly, like a breeze altering the course of a leaf, but for the most part, it follows the silent currents of the galaxy, an uncharted course through cosmic backwaters. The only light comes from distant stars, so far away they're little more than faint pinpricks in the dark, offering no warmth, no comfort. And yet, against all odds, this planet might not be as lifeless as it seems. Beneath its frozen crust, geothermal heat from radioactive decay or the slow flexing of tidal forces could maintain vast, hidden oceans. These subterranean seas, sealed away from the killing cold above, might churn with currents warmed by the planet's own internal fire. If life exists there, it would be unlike anything we know. Organisms adapted not to sunlight, but to perpetual darkness and crushing pressure, thriving in conditions that would seem impossible anywhere else. The rogue planet's journey is measured in eons. It might drift for longer than stars live, longer than entire civilizations rise and fall, and with no atmosphere to erode its surface, no solar wind to wear it down, it could remain nearly unchanged for billions of years, a relic of an ancient cosmic upheaval. Somewhere out there, right now, one of these nomad worlds could be passing through the void, carrying secrets we've only begun to guess at. Its voyage is lonely, yes, but it's also a testament to the universe's boundless creativity, a reminder that life, in whatever form, might find a way in even the darkest corners of existence. Could life exist on a world without sunlight, where the surface is a frozen wasteland and the only warmth comes from deep within? Rogue planets challenge everything we thought we knew about the conditions necessary for life. On Earth, we've discovered organisms thriving in the most hostile environments, bacteria boiling in acidic hot springs, microbes surviving in radioactive waste, even tiny creatures called tardigrades enduring the vacuum of space. If life can cling to existence in these extreme places, why not beneath the icy shell of a rogue planet, where geothermal vents might churn out heat and nutrients? Beneath miles of ice, a rogue planet's hidden ocean could be a bustling alien ecosystem. Picture a vast, lightless sea, warmed not by the sun, but by the slow decay of radioactive elements in the planet's core or the gravitational squeeze of a massive moon. Here, in the eternal dark, life wouldn't rely on photosynthesis, but on chemosynthesis, a process where microbes convert heat and chemicals into energy, just like the tube worms and bacteria thriving near Earth's hydrothermal vents. These deep-sea oases prove that life doesn't need sunlight, it just needs liquid water, a source of energy, and the right building blocks. A rogue plan, its underground ocean, could check all those boxes. Then there's the question of time. Some rogue planets may have been drifting for billions of years, their internal heat slowly fading, but others, especially larger, more massive worlds, could retain enough warmth to keep their subsurface oceans liquid for eons. Jupiter's moon Europa and Saturn's Enceladus, both icy worlds with hidden oceans, show that even small bodies can stay geologically active far from the sun. A rogue planet, free from the chaotic gravitational tugs of a star system, might offer even more stability, giving life the chance to arise, adapt, and persist in ways we can barely fathom. The real mind-bender, these planets might not just harbor life, they could spread it. If a rogue planet passed through a star system, even briefly, it could exchange material with other worlds via comets or debris. Microbes buried deep in its ice might survive the journey, seeding life across the galaxy like a cosmic pollen. It's a wild idea, but not impossible. After all, we found Earth rocks on the Moon and Martian meteorites in Antarctica, proof that the universe has a way of shuffling the deck. So while rogue planets may seem like the loneliest places in existence, they could be anything but. Beneath their frozen surfaces, entire ecosystems might pulse with alien life, unseen and unsuspected. And if that's true, the galaxy could be teeming with hidden worlds, each carrying its own secrets in the dark. The search for life beyond Earth just got a whole lot bigger and stranger. Bioluminescent tendrils pulse gently in the endless dark, casting an eerie glow through waters untouched by sunlight. This could be the reality of life on a rogue planet, where evolution takes a radically different path in the absence of stars. Picture organisms that don't just survive the darkness, they weaponize it. On Earth, creatures like the anglerfish use natural lanterns to lure prey in the abyss. On a rogue world, entire ecosystems might communicate or hunt through shimmering patterns of living light, turning the ocean into a mesmerizing light show unseen by any eyes but their own. The parallels to Earth's deep-sea vents are striking, but with a twist. In our oceans, life clusters around hydrothermal vents, thriving on chemical energy rather than sunlight. On a rogue planet, these vents could be the beating heart of an alien biosphere, except here, with no tectonic activity from a nearby star. The heat might come from slower, more persistent sources. Radioactive minerals decaying in the core could keep subsurface oceans liquid for billions of years, creating stable environments where life evolves in ways we've never witnessed. Imagine blind, jelly-like creatures drifting through warm currents, their bodies tuned to detect the faintest vibrations or shifts in water chemistry. Or perhaps armored filter feeders, clinging to rocky outcrops near mineral-rich geysers, their metabolisms running on reactions we haven't even named yet. Then there's the question of scale. Without predators adapted to sunlight, no sharks, no birds, no surface-dwelling hunter's life here might grow to sizes unimaginable in Earth's oceans. Giant, slow-moving behemoths could dominate these lightless seas, their massive bodies sustained by the planet's steady geothermal buffet. Or the opposite could be true. Life might shrink to microscopic efficiency, with entire food chains built around single-celled organisms that recycle nutrients in near-perpetual cycles. But the most fascinating possibility, symbiosis taken to extremes. On Earth, bacteria and tube worms share an unbreakable bond at hydrothermal vents. On a rogue planet, whole species might merge into tangled, cooperative networks, sharing energy so thoroughly that the line between organism and ecosystem blurs. Picture vast, living mats covering the ocean floor, a single entity in a million different forms, pulsating with collective survival. This isn't just speculation, it's a challenge to our assumptions. If life can flourish in such isolation, then the galaxy's loneliest worlds might be its most fertile. Every rogue planet drifting unseen could be an ark of biodiversity, a testament to life's refusal to surrender, even in the darkest corners of existence. And if we ever find proof, it won't just rewrite biology textbooks, it'll redefine what it means to be alive. Tidal heating is the unsung hero of rogue planets, a hidden furnace that could keep these drifting worlds alive long after their ejection into the cold abyss. Picture a planet with a massive moon locked in a gravitational dance, their mutual pull stretching and compressing the planet's interior like kneading dough. This constant flexing generates friction, and friction means heat, enough to melt ice into vast subsurface oceans, even in the absence of a star. Jupiter's moon, Europa, is the perfect example. Though it orbits a star, its subsurface ocean stays liquid not from sunlight, but from the relentless tidal tug of war with Jupiter and its neighboring moons. Now imagine that same process on a rogue planet, where a lone moon's gravity becomes the sole source of warmth in an otherwise frozen existence. The math behind tidal heating is as elegant as it is powerful. The gravitational pull between two orbiting bodies isn't uniform. It's stronger on the near side and weaker on the far side, creating a stretch and release effect. For a rogue planet with a sizable moon, this means its core and crust are continuously worked like putty, generating internal heat that seeps upward. Over time, this energy could maintain liquid water beneath miles of ice, creating pockets of habitability where life might cling. Even without a moon, a rogue planet passing close to a star or another massive object could experience temporary tidal heating, sparking brief but intense geological activity. But here's where it gets even wilder. Some rogue planets might not need moons at all. Binary rogue planets, two worlds orbiting each other in the void, could generate tidal heat through their mutual gravitational pull. Think of it as a cosmic partnership where each planet keeps the other warm through their endless waltz. The heat output might be modest compared to stellar radiation, but over billions of years, even a trickle of warmth could be enough to sustain subterranean ecosystems. The implications are staggering. If tidal heating can transform a frozen rogue planet into a potential haven for life, then the galaxy's loneliest worlds might be far more than dead relics. They could be stealthy incubators, their hidden oceans teeming with organisms adapted to a reality without sunrises or seasons. Europa's vents, spewing minerals into its dark ocean, hint at what might be possible. Now scale that up to a rogue planet, where the only limit to life's creativity is the depth of the ice and the patience of time. The more we learn about tidal forces, the clearer it becomes the universe doesn't need stars to craft habitable worlds. Sometimes, all it takes is the right dance partner. Most planets we've discovered orbit stars dutifully circling their suns in predictable paths, their existence revealed by the rhythmic dimming of starlight or the wobble of their host star's position. But rogue planets defy this orderly arrangement. Untethered from any star, they drift through interstellar space like cosmic nomads, invisible to the traditional methods that have catalogued thousands of exoplanets. This fundamental difference isn't just about location. It reshapes everything from how we find these worlds to whether they could possibly harbor life. Take detection first. Finding an exoplanet orbiting a star is like spotting a moth near a streetlight. The contrast makes it visible. Astronomers watch for the moth's shadow, the transit method, or the way its tiny gravity makes the streetlight sway, the radial velocity method. But rogue planets have no streetlight. They're moths flying through total darkness, detectable only when their gravity briefly warps the light of a distant background star, a fleeting phenomenon called microlensing that requires perfect cosmic alignment. Even then, we might only get one chance to observe them before they vanish back into the void. Then there's the question of habitability. Exoplanets in the Goldilocks zone, the region around a star where temperatures allow liquid water, dominate our search for alien life. But rogue planets rewrite the rules. Without sunlight, their surface temperatures plunge hundreds of degrees below freezing, making surface life as we know it impossible. Yet beneath miles of ice, geothermal heat or tidal forces could maintain vast underground oceans. While Earth-like exoplanets need the right distance from their star, rogue planets create their own habitable zones internally, turning the concept of a Goldilocks zone inside out. The implications for astrobiology are staggering. Traditional exoplanets offer environments we recognize worlds with days and nights, seasons, and weather patterns driven by stellar energy. Rogue planets present ecosystems completely divorced from these rhythms, where life, if it exists, would rely on chemosynthesis in perpetual darkness. Imagine organisms that have never experienced sunlight, evolving over billions of years in isolation, their biology shaped by entirely different evolutionary pressures. While exoplanets might host life similar to Earth's, rogue planets could harbor forms of existence we've never imagined. Scientific interest splits along similar lines. Exoplanet research focuses on diversity-hot Jupiters, super-Earths, ocean worlds, all variations on the theme of planets bound to stars. Rogue planet studies push into uncharted territory, probing questions about planetary formation and ejection, the stability of dark energy atmospheres, and the extremes of cosmic solitude. Every new rogue planet discovery forces us to reconsider what planet even means. Are they failed stars, ejected orphans, or something else entirely? Perhaps the most profound difference lies in longevity. Exoplanets live and die with their stars. When a sun goes red giant or collapses, its planets perish. But rogue planets, untethered from stellar life cycles, could persist for trillions of years, carrying potential life through epochs when all other worlds have frozen over. They're not just oddities, they might be the universe's ultimate survivors, silent witnesses to cosmic evolution long after the stars themselves have faded. The Milky Way may be teeming with planetary nomads, rogue worlds that outnumber stars by an astonishing margin. Recent studies suggest there could be billions of these drifters lurking unseen in our galaxy, far exceeding previous estimates. Some models propose that for every star shining in the night sky, there are at least 20 rogue planets gliding silently through the darkness. That means trillions could be scattered across the observable universe, a staggering thought when you consider how few we've actually detected. Why so many? The answer lies in cosmic chaos. When solar systems form, gravitational battles between young planets often end with losers, smaller worlds, flung into the void like stones from a slingshot. Simulations show that a single star's birth can eject multiple planets, and with hundreds of billions of stars in the Milky Way, the math quickly adds up. But not all rogue planets start as exiles. Some may form directly from collapsing gas clouds in deep space, never knowing the warmth of a star. These failed stars, or sub-brown dwarfs, blur the line between planet and star, adding to the cosmic census of untethered worlds. The implications for life are profound. If even a fraction of these rogue planets harbor subsurface oceans heated by tidal forces or radioactive decay, the galaxy could be filled with pockets of habitability we've never considered. Imagine billions of dark refrigerators, each potentially preserving life in icy suspension for eons. While Earth-like planets need the perfect distance from their star, rogue worlds create their own habitable zones internally, turning the traditional search for life on its head. But detecting them remains a colossal challenge. Gravitational microlensing events, our primary tool, are fleeting and rare, like catching a single frame in a century-long movie. The upcoming Nancy Grace Roman Space Telescope could change that, scanning for microlensing signals with unprecedented precision. Every new detection rewrites the rules, hinting that we've barely scratched the surface of this invisible population. So while stars guide our maps of the cosmos, rogue planets might be its true silent majority. Their abundance suggests that life, if it exists out there, isn't confined to cozy orbits around suns. It could be thriving in the coldest, darkest reaches of space, hidden beneath ice and time. The more we learn, the clearer it becomes. The universe doesn't just favor life in Goldilocks zones. It sows the seeds of survival everywhere, even in the endless night between the stars. Imagine a rogue planet, ice-covered and dark, drifting silently between the stars for billions of years. Now picture it passing just a little too close to a young, habitable world, close enough for gravity to pull fragments of its icy shell into space, where they fracture into comets. Those comets, glowing faintly as they streak toward the new planet's surface, could be cosmic delivery trucks carrying something extraordinary, the seeds of life. This isn't just wild speculation, it's a serious scientific idea called panspermia, and rogue planets might be its ultimate transporters. The math is startlingly plausible. We know from meteorites like the Murchison specimen that organic molecules, even amino acids, can survive the harshness of space. If a rogue planet's subsurface ocean harbored microbes, impacts or cryovolcanic eruptions could blast them into space encased in protective ice. Once ejected, radiation-resistant organisms like tardigrades or extremophile bacteria might endure the journey, frozen in suspended animation. The vacuum of space would pause their metabolism, while the ice shielded them from cosmic rays. Then, if their icy vessel collided with a world like early Earth, the heat of atmospheric entry could melt just enough ice to release them into a welcoming ocean. But here's where the debate ignites. Critics argue the odds are vanishingly slim. A rogue planet would need to pass unusually close to another star system for material exchange, and even then, most microbes would perish during ejection or re-entry. Yet supporters counter that given enough time, and the universe operates on timescales we can barely fathom, even unlikely events become inevitable. Consider this: if just one in a trillion rogue planets successfully transferred life, there could still be hundreds of successful, seeding events across the Milky Way alone. The kicker: we might already have evidence this happens. In 2019, astronomers detected two interstellar objects, Oumuamua and Comet Borisov, passing through our solar system. While neither were rogue planets, their existence proves material does migrate between star systems. Extend that logic to trillions of drifting worlds, and the numbers start to feel less like science fiction and more like a cosmic inevitability. Perhaps most intriguing is the role rogue planets could play in life's spread versus its origin. Even if life only arose once in the universe, these nomadic worlds might have distributed it everywhere, turning the galaxy into a vast network of interconnected biospheres. It's a humbling thought that life on Earth, and possibly ourselves, could owe its existence to a long-forgotten rogue planet, a cosmic vagabond that passed through our neighborhood billions of years ago, leaving behind the faintest spark in the darkness. On Earth, we found life thriving in places once thought uninhabitable, places where the sun's rays never reach, where temperatures swing from boiling to freezing, and where the very chemistry would be lethal to most surface-dwelling organisms. These extremophiles, as they're called, rewrite the rules of biology, proving that life doesn't need sunlight to flourish. Instead, they rely on something far more primal: chemical energy. Deep in the ocean trenches, around hydrothermal vents known as black smokers, entire ecosystems thrive in total darkness, powered not by photosynthesis, but by chemosynthesis. Here, bacteria convert hydrogen sulfide and other minerals spewing from the vents into usable energy, forming the base of a food chain that supports towering tube worms, ghostly crabs, and otherworldly creatures adapted to a realm untouched by the sun. This process, chemosynthesis, could be the blueprint for life on a rogue planet. Imagine a world where geothermal vents pepper the floor of a subsurface ocean, their mineral-rich plumes feeding microbes that, in turn, sustain larger organisms. Without sunlight, evolution would take radical detours. Creatures might develop heightened sensitivity to heat or chemical gradients, navigating their environment through senses we can barely comprehend. Some could harness bioluminescence, not just for attraction or predation, but as a way to communicate in the perpetual dark, their bodies flickering like submerged constellations. But chemosynthesis isn't the only alternative to sunlight. On Earth, scientists have discovered microbes living miles underground, surviving on nothing but the faint energy released by radioactive decay in rocks. These subsurface lithoeutotrophic microbial ecosystems, or S-LIME, get their energy from breaking down minerals like pyrite, essentially eating stone. If life can eke out an existence in the pores of deep Earth rocks, why not beneath the icy crust of a rogue planet, where radioactive elements in the core could provide a steady trickle of energy for billions of years? Then there's the wild card, alternative biochemistries. While Earth life relies on water, carbon, and familiar elements, rogue planets might host organisms built on entirely different foundations. Ammonia-based life could thrive in colder temperatures, its chemistry tuned to the slow, deliberate rhythms of a frozen world. Or perhaps life there would exploit methane or hydrogen, using reactions alien to our own biology. The deeper we look into Earth's extremes, the more we realize life is a shapeshifter, adapting to whatever energy sources are available. The lesson is clear: sunlight isn't life's only lifeline. From the crushing depths of our oceans to the fractured bedrock beneath our feet, organisms have found ways to thrive in the unlikeliest places. If life can persist here, under such brutal conditions, then rogue planets, with their hidden oceans and geothermal whispers, might not be the barren wastelands we once imagined. They could be cosmic arcs, carrying ecosystems forged in darkness, each one a testament to life's relentless ingenuity. The hunt for rogue planets and the tantalizing possibility of life they carry is entering a revolutionary new phase. Until recently, these cosmic drifters were nearly invisible, glimpsed only through fleeting microlensing events or faint thermal signatures. But cutting-edge missions like the Nancy Grace Roman Space Telescope, set to launch in the next few years, promise to change everything. With a field of view 100 times wider than Hubble's infrared instruments, Roman will scan vast stretches of the galaxy, not just for rogue planets themselves, but for the subtlest hints of what might lurk beneath their frozen surfaces. One game-changing approach, studying microlensing events with unprecedented precision. When a rogue planet passes in front of a distant star, its gravity bends the starlight like a lens, creating a brief brightening that betrays its presence. Roman's advanced optics can measure these events down to the tiniest fluctuations, clues that might reveal an atmosphere, or even the thermal glow of hidden geothermal activity. Imagine detecting water vapor or methane escaping from cryovolcanoes, hints of a subsurface ocean venting into space. These wouldn't just be planet detections, they'd be windows into alien geochemistry. But Roman is just the beginning. Future missions like Europe's Euclid telescope or the proposed habitable exoplanet observatory could take the search even further. By analyzing the infrared spectra of rogue planets, scientists might spot molecular oxygen or other potential biosignatures, gases that, on Earth, are almost exclusively produced by life. The challenge: distinguishing these signs from geological processes. A rogue planet with tidal heating might mimic biological activity, venting gases through cracks in its icy shell. That's where next-gen tools like quantum dot-based spectrometers come in, capable of identifying complex organic molecules with unheard of accuracy. Then there's the wild card, direct imaging. Projects like NASA Origins Space Telescope concept aim to block starlight so effectively that even the dimmest rogue worlds could be photographed. A single pixel of thermal contrast might reveal surface cracks spewing warm water, or the infrared halo of a thick, heat-trapping atmosphere. Combined with AI-driven data analysis, these missions could sift through millions of cosmic snapshots, flagging the most promising candidates for life. The ultimate dream, a dedicated interstellar probe like Breakthrough Starshot's nanocraft, someday flying past a rogue planet to sample its plumes. Until then, each new telescope brings us closer to answering an ancient question: are we alone? The answer might not come from a distant star, but from the frozen, forgotten worlds drifting silently in the dark. What if rogue planets aren't just accidental wanderers, but intentional vessels, engineered by civilizations so advanced they've mastered interstellar travel on a planetary scale? The concept sounds like science fiction, but the physics is startlingly plausible. Picture a species facing an existential crisis, their star dying, their system unstable, choosing not to abandon their world, but to take it with them. By harnessing the gravitational slingshot of passing stars or deploying vast propulsion systems, they could nudge their planet just enough to eject it from orbit, setting course for another star system over tens of thousands of years. Far slower than conventional spacecraft, yes, but with an unbeatable advantage, carrying an entire biosphere intact, complete with cities, ecosystems, and generations of inhabitants living out their lives in transit. This isn't just theoretical. On a cosmic timescale, rogue planets do occasionally pass near stars close enough for a brief gravitational encounter before drifting onward. An advanced civilization could plot these chaotic trajectories, using them as free boosts to steer their world toward a distant destination. The journey would span millennia, but for a species thinking in deep time, that's a manageable horizon. Inside the planet, layers of artificial insulation and geothermal taps could maintain surface habitation, while enormous mirrors or fusion reactors simulate sunlight during the coldest stretches between stars. The ultimate generational ship wouldn't be a cramped metal ark, it'd be a modified planet, its entire mass repurposed as a lifeboat. The implications are staggering. If such nomadic civilizations exist, they'd be virtually undetectable by our current methods. No radio signals, no Dyson swarms, just a silent, Earth-sized object coasting through the dark. Their technology might leave subtler traces, unnatural atmospheric compositions, geometric surface patterns, or even heat signatures from subsurface industry. Future telescopes scanning rogue planets for biosignatures could stumble upon something far more startling: technosignatures, hints of intelligence buried beneath the ice. Then there's the darker possibility. What if some rogue planets aren't arcs, but weapons? A world deliberately flung into another star system could trigger mass extinctions, its gravity destabilizing orbits or pulling comets into catastrophic collisions. Galactic warfare at this scale would play out over eons, with civilizations treating planets as kinetic projectiles in a slow-motion siege. Far-fetched. Perhaps, but the universe has had billions of years for such nightmares to unfold. Whether arcs, weapons, or something beyond our imagination, rogue planets challenge our assumptions about intelligence in the cosmos. They force us to ask, could the most advanced civilizations be the ones we never see coming, not because they're hiding, but because they've become the very worlds drifting past us in the night? The answer might rewrite not just our search for life, but our place in a universe where planets themselves could be conscious travelers. Rogue planets have long captured the imaginations of storytellers, becoming the perfect backdrop for tales of isolation, survival, and cosmic wonder. In Star Wars, The Force Awakens, Starkiller Base isn't just a weapon, it's a rogue planet converted into a mobile fortress, harnessing the energy of entire stars. The chilling concept of a world that can move through space, devouring suns, plays on our deepest fears of the unknown. Then there's The Wandering Earth, a Chinese sci-fi epic where humanity literally straps engines to Earth to escape our dying sun, turning our home into a rogue planet on a desperate exodus. Both stories tap into the same haunting question: what happens when a world loses its star? But science fiction often bends the rules. While real rogue planets drift in perpetual cold, fictional versions sometimes defy physics to serve the plot. Doctor Who's The Impossible Planet features a world orbiting a black hole, technically impossible without tidal forces tearing it apart. Yet the episode thrives on the eerie tension of a civilization clinging to the edge of oblivion. These creative liberties shape public perception, making rogue planets seem more like supernatural entities than natural cosmic phenomena. Literature dives deeper into the psychological weight of these nomad worlds. In Alastair Reynolds' Revelation space novels, rogue planets are forgotten relics of ancient wars, their surfaces scarred by long-dead civilizations. They're not just settings, they're silent witnesses to cosmic history, carrying secrets older than stars. Meanwhile, Liu Cixin's The Three-Body Problem explores a rogue planet caught in a chaotic three-star system, where unstable orbits mirror the existential dread of its inhabitants. These stories amplify the real science, tidal forces, extreme cold, and isolation into metaphors for humanity's fragility. The influence on pop culture is undeniable. Films like Interstellar flirt with rogue planet concepts, blending real astrophysics with heart-wrenching drama. When Cooper's crew lands on Miller's planet, a world crushed by a black hole's gravity, the time dilation effect, where hours equal years elsewhere, is rooted in real relativity. Yet the emotional core, the cost of lost time, resonates because it's grounded in human stakes. What's fascinating is how these portrayals loop back into science. Public fascination with rogue planets, sparked by fiction, fuels real-world research funding. When The Wandering Earth became a box office hit, astronomers noted a surge in questions about planetary ejection and interstellar travel. Sci-fi doesn't just reflect our fears, it primes us to see these drifting worlds not as dead rocks, but as frontiers. The line between fiction and reality blurs, and suddenly, the search for rogue planets isn't just academic. It's a hunt for the next great cosmic story. The universe holds mysteries so profound they bend our understanding of reality. None more puzzling than dark matter, the invisible glue holding galaxies together. We can't see it, can't touch it, yet its gravitational fingerprints are everywhere. Now, imagine a possible culprit hiding in plain sight: rogue planets. These untethered worlds, drifting unseen by the trillions, might just be the missing piece of the dark matter puzzle. For decades, scientists calculated that visible matter, stars, gas, dust accounts for a mere 15% of the universe's gravity. The rest, that's dark matter's domain. But traditional candidates, like WIMP or ACTIONS, remain frustratingly undetected despite decades of searching. Enter rogue planets. If they exist in the numbers some theories suggest, their combined mass could be staggering. Picture this: billions of Jupiter-sized worlds, each 50 times Earth's mass, lurking in the voids between stars. Collectively, they might contribute enough heft to explain at least a fraction of dark matter's gravitational effects. Here's where it gets thorny. Even if rogue planets are abundant, there's a catch. They are made of ordinary matter, the same protons and neutrons we're made of. Dark matter, by definition, doesn't interact with light or normal matter except through gravity. So how could rogue planets be part of the solution? The answer lies in their stealth. These worlds are so cold, so faint, they're practically invisible to telescopes. From our perspective, they might as well be dark matter, ghostly anchors tugging on galaxies without revealing themselves. But the math doesn't quite add up. Even the most optimistic estimates suggest rogue planets could only account for a sliver of dark matter's total mass. Their distribution is another hurdle. Dark matter envelops galaxies in vast halos, while rogue planets would likely cluster differently, some lingering in galactic outskirts, others adrift in intergalactic space. Then there's the question of formation. If rogue planets were numerous enough to explain dark matter, we'd expect to see more microlensing events than we currently do. The numbers just aren't there, yet the idea refuses to die because rogue planets might not be acting alone. Some theorists propose a hybrid solution. What if certain rogue planets aren't made of normal matter at all? Hypothetical objects like primordial black holes, forged in the chaos of the Big Bang, could masquerade as rogue planets. These wouldn't reflect or emit light, fitting dark matter's elusive profile perfectly. Others speculate about mirror matter planets, composed of exotic particles that barely interact with our universe. It's a long shot, but in the quest to solve cosmology's greatest riddle, every possibility deserves a glance. The real value of this theory isn't in its answers, it's in the questions it forces us to ask. If rogue planets can't fully explain dark matter, their sheer abundance still reshapes our cosmic accounting. Every drifting giant we discover reminds us how much of the universe remains hidden, how much mass might be tucked away in plain sight, and who knows? Maybe future telescopes will unveil a stranger truth that dark matter wasn't one mystery, but many, with rogue planets playing a role we can't yet fathom. Until then, they linger at the edge of our understanding, silent and shadowy, much like the dark matter they might, or might not help explain. If rogue planets are as abundant as the latest research suggests, outnumbering stars by 20 to 1, then where are all the aliens? This question lies at the heart of the Fermi paradox, the baffling contradiction between the high probability of extraterrestrial life and the complete lack of evidence for it. Rogue planets, with their potential to harbor subsurface oceans and exotic ecosystems, should, in theory, be galactic way stations for advanced civilizations. They offer nearly limitless real estate, protection from stellar catastrophes, and longevity measured in trillions of years. So why does the cosmos seem so silent? One possibility is that life on rogue planets exists, just not in ways we recognize. Traditional searches for aliens focus on radio signals or Dyson swarms, technologies that assume a species needs stars for energy. But a civilization evolving in the perpetual dark of a rogue planet would develop radically different solutions. Their energy might come from deep geothermal taps or nuclear fission, their communications encoded in neutrino pulses or quantum entanglement. To them, the electromagnetic spectrum might be as foreign as smoke signals are to us. We're not just looking for aliens in the wrong places, we might be looking with the wrong tools. Then there's the timescale problem. Rogue planets drift for billions of years, far longer than most stars last. A civilization arising on one would have no urgency to expand or signal its presence. While Earth-bound societies race against stellar life cycles, rogue planet dwellers could afford to move at a glacial pace, their ambitions unfolding across epochs. By the time they reach technological maturity, the stars we see today might have long since burned out, leaving their descendants isolated in a darkening universe. The paradox isn't that they don't exist, it's that their timelines are so vast, our civilizations barely overlap, but the darkest explanation, rogue planets might be traps. Imagine a world where life emerges in a subsurface ocean, evolves intelligence, and even develops spaceflight only to hit an insurmountable barrier. Breaking through miles of ice to reach the void would require energy and engineering far beyond escaping Earth's gravity. And even if they succeeded, the nearest star might be light years away, with no guarantee of habitable destinations. Such a civilization could be forever imprisoned beneath the ice, their genius funneled into survival rather than expansion. The universe might be teeming with trapped minds, their potential forever unrealized. This adds a chilling twist to the Fermi paradox. The silence isn't just about distance or technology, it's about physics itself conspiring against life's spread. Rogue planets offer refuge, but they might also be cosmic quarantine zones, their inhabitants doomed to contemplate the stars without ever reaching them. Or perhaps we're the odd ones, born in the light of a star, while most intelligence thrives in the dark, unseen and unconcerned with our search. Either way, these nomad worlds force us to reconsider not just where life might be, but what form it takes when cut off from the sky forever. Among the countless rogue planets adrift in the galaxy, a handful have been detected surprisingly close to Earth's cosmic neighbors lurking in the darkness, just light years away. One of the most intriguing is CF21b, a potential rogue world floating roughly 20 light-years from our solar system. Discovered through infrared observations, this Jupiter-sized nomad emits a faint thermal glow, a remnant of its formation heat slowly dissipating into space. What makes CF21b special isn't just its proximity, it's the tantalizing hint of an ammonia-rich atmosphere, a chemical cocktail that could insulate the planet enough to sustain subsurface warmth. If confirmed, it would be the closest known rogue planet with conditions that might harbor life beneath its frozen shell. Then there's SIMP J0136566+09+33, a rogue planet candidate a mere 20 light-years away in the constellation Aquarius. This one defies expectations. Despite its rogue status, it behaves more like a star than a planet, radiating a surprising amount of heat for its size. Some scientists speculate it could be a failed star, a brown dwarf too small to ignite fusion, but massive enough to generate internal heat for billions of years. Others argue it's a true rogue planet, ejected from its system with a radioactive core or tidal heating keeping it anomalously warm. Either way, its extreme environment challenges our definitions of what a planet even is. But the most startling discovery might be the tiny wanderer known as Ogle 2016 BLG 1928. Located an estimated 8,000 light-years away, this Earth-sized rogue is one of the smallest ever detected. Its discovery via microlensing was a cosmic fluke, a perfect alignment with a distant star that lasted mere hours. What's revolutionary about this find isn't its distance, but its size. If Earth-mass rogue planets are common, the galaxy could be teeming with trillions of them, far more than we ever imagined. Some might even be stripped-down remnants of rocky worlds, their atmospheres ripped away during ejection, leaving behind barren cores drifting endlessly. The significance of these nearby rogue planets isn't just academic. Each one is a natural laboratory, testing the limits of planetary science. CF21b could teach us about exotic atmospheres in extreme cold. SIMP J0 136566 plus 09 plus 33 blurs the line between planet and star, forcing us to rethink how celestial objects form. And Ogle 2016 BLG 1928 suggests that rogue planets come in all sizes, perhaps even some with conditions eerily similar to early Mars, frozen in time. Yet for all we've learned, these detections are just the tip of the iceberg. Current methods only catch the largest, warmest, or most fortuitously aligned rogue planets. The closest Earth-like rogue could be just a few light-years away, invisible to our telescopes, waiting for future technology to reveal it. Every new discovery peels back another layer of the mystery, hinting at a galaxy far more crowded with nomad worlds than we ever dreamed. And if even one of them carries life, the implications would echo across the cosmos. The idea of Earth breaking free from the sun's grasp and hurtling into interstellar space sounds like the plot of a doomsday blockbuster, but in the grand chaos of the cosmos, it's not entirely impossible. To understand how our planet could go rogue, we need to peer into the violent forces that shape solar systems. Picture this: a passing star, far more massive than our Sun, streaks uncomfortably close to our solar system. Its gravitational pull tugs at the planets like an invisible hand, disrupting their orbits. In this cosmic game of pinball, Earth could be sent careening outward, stripped of the sun's warmth and light in an instant. The odds are astronomically low, but over the span of billions of years, even the unlikeliest events can unfold. The immediate aftermath would be apocalyptic. Without the sun, photosynthesis would cease within weeks, collapsing the food chain from the ground up. Global temperatures would plummet at a staggering rate within months. The surface would become colder than Antarctica, with atmospheric gases freezing into snowfall. The oceans would gradually freeze solid, trapping marine life beneath thickening ice. Hurricanes of frozen nitrogen might rage across the continents, scouring the barren landscape. Within a few short years, Earth's surface would become an airless wasteland, a ghost of its former self. Yet beneath the ice, there's a sliver of hope. Earth's core, heated by radioactive decay and residual planetary formation energy, would remain molten for billions of years. This internal furnace could sustain pockets of liquid water deep underground, much like the subsurface oceans of Jupiter's moon Europa. Hydrothermal vents, already teeming with extremophiles on our ocean floors, might become the last refuges for life. Microbes adapted to extreme pressure and heat could persist in these isolated oases, evolving in slow motion over geologic time. Human survivors, if any remained, would need to retreat to geothermal bunkers, tapping into the planet's inner heat for energy, while synthetic ecosystems struggled to replace the lost biosphere. The long-term survival of Earth as a rogue planet hinges on its ability to retain an atmosphere, or lack thereof. Without the sun's radiation pressure, solar wind would no longer strip away our protective layers, but extreme cold would cause gases to condense and freeze. A thick ice shell could ironically act as insulation, sealing in warmth and volatile compounds. Alternatively, tidal forces from the moon, assuming it stays bound to Earth, might generate enough friction to keep subsurface environments active. Over eons, Earth could transform into a frozen ark, its biosphere reduced to microbial survivors clinging to the last whispers of geothermal energy. The most haunting question isn't whether Earth could become a rogue planet, it's whether we'd even recognize it afterward. Stripped of its blue skies and green landscapes, our world would become a silent, icy tomb, drifting through the void with only the faint glow of distant stars to illuminate its frozen deserts. And yet, in the unimaginable darkness, life might still flicker in the deep, a testament to its stubborn will to endure. The universe is unpredictable, and while the chances are slim, the mere possibility forces us to confront a humbling truth. Even a planet as vibrant as Earth is just one gravitational nudge away from becoming another cosmic wanderer. Rogue planets don't just haunt the Milky Way, they could be adrift in every corner of the universe, lurking in the vast expanses between galaxies. The idea isn't just speculation, it's a mathematical certainty. When solar systems form, gravitational chaos ejects planets like cosmic shrapnel, and with hundreds of billions of galaxies, each hosting trillions of stars, the numbers add up fast. But detecting these intergalactic wanderers is another story entirely. The Milky Way's rogue planets are hard enough to spot, and those in distant galaxies are like finding a single grain of sand in an ocean of darkness. Take Andromeda, our nearest galactic neighbor. At 2.5 million light-years away, even its stars appear as faint pinpricks. A rogue planet there, with no star to illuminate it, would be virtually invisible to current telescopes. Microlensing, our go-to method for finding rogue worlds in the Milky Way, becomes astronomically harder across such distances. The alignment required, a rogue planet passing precisely between us and a background star in Andromeda, is so improbable it makes winning the lottery look like a sure bet. Even if it happened, the lensing signal would be drowned out by the glare of Andromeda's billion other stars. Then there's the redshift problem. As the universe expands, light from distant galaxies stretches into longer, redder wavelengths. Infrared telescopes like James Webb can peer through this cosmic haze, but rogue planets are already cold, emitting minimal heat. By the time their faint thermal radiation reaches us, it's often lost in the noise of interstellar dust and background radiation. It's like trying to spot a dying ember in a forest fire. The sheer scale of the universe works against us. Yet hope isn't lost. Some astronomers propose looking for rogue planets indirectly through their gravitational footprints. In galaxy clusters, where thousands of galaxies swirl together, the collective gravity bends light like a funhouse mirror, an effect called strong lensing. Hidden within these distorted images could be the subtle warping caused by rogue planets, their mass subtly twisting the light of more distant objects. It's a long shot, but with machine learning algorithms sifting through petabytes of data, we might one day find these cosmic ghosts hiding in plain sight. The real game changer could come from rogue planets in the voids between galaxies. These desolate regions, nearly empty of stars, might seem like the last place to look. But recent simulations suggest that trillions of rogue planets could be floating in these abysses, ejected during galactic collisions billions of years ago. Without the glare of nearby stars, these isolated worlds might actually be easier to study if we can ever reach them. Future missions like the Laser Interferometer Space Antenna could detect their gravitational waves, ripples in spacetime caused by massive rogue planets orbiting each other in the darkness. What's at stake goes beyond curiosity. If rogue planets are common in other galaxies, it suggests that planet ejection isn't just a quirk of the Milky Way, it's a universal process. That means life, if it exists out there, might not be confined to cozy orbits around stars. It could be clinging to survival in the cold, dark reaches between galaxies, thriving in ways we've yet to imagine. The universe has a habit of being stranger than fiction, and rogue planets in distant galaxies might be its most enigmatic nomads yet. The next decade could shatter everything we thought we knew about rogue planets, not just through better telescopes, but through an entirely new way of seeing the cosmos. The upcoming Nancy Grace Roman Space Telescope, launching in late 2026, will act like a cosmic census taker, scanning the galaxy for microlensing events with unprecedented precision. But here's the breakthrough. Roman won't just spot rogue planets, it'll map their distribution, revealing whether they cluster near star-forming regions or drift uniformly through interstellar space. This data could settle one of astronomy's biggest debates. Are most rogue planets ejected orphans, or did they form alone in the dark? Meanwhile, the European Space Agency's Euclid mission is taking a different approach. Using infrared optics sharper than any before it, Euclid will hunt for the faint thermal glow of young rogue planets still warm from formation, the real innovation. Its ability to detect objects as small as Mars, pushing the boundaries of what we consider a planet. But the game changer lies in combining these missions with AI. Machine learning algorithms, trained on simulated rogue planet signatures, will sift through petabytes of data in days' work that would take human researchers centuries. These systems might uncover patterns invisible to us, like subtle atmospheric signatures or the gravitational fingerprints of rogue planets with moons. Then there's the wild card, quantum sensing. Researchers are developing detectors that exploit quantum entanglement to measure gravitational distortions with nanometer precision. In theory, these could spot Earth-mass rogue planets from thousands of light-years away by sensing the space-time ripples they create as they drift, no starlight required. It's like turning the entire galaxy into a gravitational microphone, listening for the faint footsteps of invisible worlds. But the most radical vision belongs to NASA's Interstellar Probe Concept, a mission designed to venture beyond our solar system, potentially flying within striking distance of a rogue planet. Equipped with submillimeter wave spectrometers, it could sniff out plumes of water vapor or organic molecules erupting from cryovolcanoes. Imagine direct sampling of an alien ocean's chemistry, light years from any star. The ultimate prize, linking these technologies to solve rogue planet's greatest mystery, habitability. Future missions might deploy neutrino telescopes to peer inside their icy shells, detecting the heat of subsurface oceans indirectly. Or swarm probes could use laser sails to reach nearby rogue worlds within decades, not millennia. What awaits us isn't just new discoveries, it's a fundamental shift in how we define a planet's potential. These nomad worlds may soon move from cosmic curiosities to prime targets in the search for life, rewriting the rules of where and how we look for our place in the universe. What if life didn't begin on Earth at all, but hitched a ride here aboard a rogue planet billions of years ago? This radical twist on panspermia, the idea that life spreads between worlds, flips our understanding of origins upside down. Most discussions of panspermia focus on comets or asteroids as cosmic couriers, but rogue planets offer something far more compelling: stability. Picture a young, water-rich rogue planet, ejected from its star system during the chaotic early days of the galaxy. Drifting through interstellar space, its subsurface ocean remains liquid thanks to geothermal heat, sheltering microbial life for eons. Then, a chance encounter with the young solar system sends it careening toward Earth, colliding or shedding icy fragments laden with organisms into our primordial oceans. Far-fetched, perhaps, but the chemistry of life's building blocks tells a tantalizing story. Consider the Murchison meteorite, a space rock that fell to Earth in 1969. Inside, scientists found amino acids, the very ingredients of proteins, along with nucleotides, the backbone of DNA. If simple chemistry in asteroids can produce life's raw materials, why not the complex, stable environments of rogue planets? Their subterranean oceans could act as cosmic laboratories, where hydrothermal vents mix minerals and gases over millions of years, allowing molecules to assemble into ever more complex structures. Unlike the harsh surface of an asteroid, bombarded by radiation, a rogue planet's ice shield might protect delicate chemical reactions long enough for life to emerge. The timing adds another layer of intrigue. Earth's oldest fossils, dating back 3.5 billion years, suggest life appeared astonishingly fast after the planet cooled. Some scientists argue this leaves too little time for life to arise from scratch. But if life originated earlier, elsewhere, say, on a rogue planet drifting through the galaxy for 1 billion years before reaching us, the timeline suddenly makes sense. Earth wouldn't be life's cradle, just its new home. Critics counter with the survival problem. Even the hardiest microbes would struggle to endure the radiation and vacuum of space for interstellar journeys. Yet nature offers startling examples of resilience. Deinococcus radiodurans, a bacterium found on Earth, can survive thousands of times the radiation dose that would kill a human. Tardigrades, microscopic water bears, enter suspended animation when dehydrated, reviving after years in space. Encased in ice deep within a rogue planet, such organisms could theoretically sleep through a journey spanning light years, waking only when their icy vessel melts into a new ocean. The most provocative idea isn't just that rogue planets could carry life, it's that they might be its original architects. In this scenario, life isn't a rare fluke, but a cosmic inevitability, arising wherever conditions permit and spreading wherever gravity allows. Earth's biosphere, then, might be part of a vast, interconnected web, with rogue planets as the invisible threads tying it together. As we search for life beyond our world, perhaps we're not just explorers, we're pilgrims, tracing the path of our own deepest origins back to the stars. Landing on a rogue planet isn't like touching down on Mars or Europa. It's more like plunging into the deepest, darkest ocean with no surface to breach. Without a star to provide warmth or light, the first challenge is simply finding the damn thing. Traditional navigation is useless. There's no orbital trajectory to calculate, no sunlit surface to aim for. Instead, a probe would rely on gravitational anomalies and faint thermal signatures, homing in on whispers of heat radiating from the planet's core. Even then, the approach would be treacherous. With no atmosphere to slow descent, any lander would need pinpoint accuracy, firing retro-thrusters with surgical precision to avoid smashing into ice cliffs or vanishing into bottomless crevices. One wrong calculation and your billion-dollar mission becomes a crater. Then comes the cold, a cold so absolute it defies earthly logic. Surface temperatures hover near -270 degrees Celsius, just a hair above absolute zero. Standard metals would turn brittle and shatter like glass, while lubricants in moving parts would freeze solid. Engineers would need exotic materials, alloys infused with graphene for flexibility, self-heating circuits woven into every component, and insulation thicker than a bank vault's door. Even the lander's camera lenses would need constant heating to prevent frost from obscuring the view. Every system would require redundant power sources because solar panels are pointless in perpetual night. Nuclear batteries or miniature fusion reactors might be the only options, their warmth a tiny beacon against the endless freeze. but the real nightmare. The ice. Rogue planets likely have surfaces harder than steel, with layers of frozen nitrogen, methane, and water forming a shell miles thick. Drilling through it would demand more than a robotic arm. It would take laser drills or plasma torches, tools usually reserved for sci-fi. And if the goal is to reach a subsurface ocean, the lander would need to be part submarine, capable of melting its way down like a nuclear-powered icicle. The pressure at those depths would be crushing, comparable to the Marianas Trench multiplied by 10. Any breach in the hull, and the entire mission implodes in milliseconds. Yet the potential payoff is staggering. Scientists would be drooling over the chance to sample a rogue planet, its hidden ocean, where geothermal vents might brew a primordial soup untouched by sunlight for billions of years. Imagine discovering microbes that metabolize sulfur or hydrogen, their biochemistry a mirror to Earth's earliest life, or something entirely alien. Spectrometers could analyze the water for organic molecules, while seismic sensors map the planet's interior, revealing whether its core still churns with enough heat to sustain liquid layers. And if by some miracle the planet has a thin atmosphere, spectrographs might sniff out gases like methane or molecular hydrogen, potential biosignatures in this lightless realm. The greatest challenge, though, isn't technical, it's temporal. With no sunlight to recharge batteries, a lander's lifespan might be measured in days or weeks. Every experiment would need to run at breakneck speed, data streaming back to Earth before the cold claims the hardware. There'd be no second chances, no do-overs. Just a single, desperate lunge into the dark, hoping to grab a few priceless clues before the void swallows the probe forever. But if it works, the mission would rewrite textbooks. A successful landing could prove that life doesn't need stars, just liquid water, energy, and time. It would turn rogue planets from cosmic oddities into prime targets in the search for alien life. And for the engineers who pulled it off, they'd deserve more than Nobel Prizes. They'd deserve statues carved from ice. What happens if we're not the first to discover life on a rogue planet, but the ones who accidentally destroy it? The ethics of exploring these nomad worlds aren't just theoretical. They force us to confront a chilling possibility. Imagine a subsurface ocean, untouched for billions of years, its alien ecosystems evolving in perfect isolation. Now picture a probe from Earth crashing through the ice, its heat sterilizing entire swaths of that pristine environment, or worse, introducing earthly microbes that outcompete native life. The contamination risk is real. We've already seen it on Mars, where NASA rovers undergo rigorous decontamination to avoid carrying hitchhiking bacteria. But rogue planets add a sinister twist. Unlike Mars, where solar radiation batters the surface, a rogue planet's icy shell could preserve Earth's contaminants indefinitely, turning our curiosity into an extinction event. Then there's the question of ownership. If we find a rogue planet teeming with life, do we have the right to alter it? Terraforming, a concept straight out of sci-fi, suddenly becomes a moral minefield. On one hand, these worlds could be humanity's ultimate lifeboats if Earth becomes uninhabitable. Melting their ice to create artificial atmospheres might seem like survival. But what if that process drowns native organisms in their own homes? The Outer Space Treaty of 1967 prohibits harmful contamination of celestial bodies, but rogue planets exist in a legal gray zone. They're not part of any star system, making them cosmic no-man's lands. Without clear laws, exploitation becomes dangerously easy. The dilemma deepens when you consider unintended consequences. Suppose we discover a rogue planet with intelligent life trapped beneath its ice. Their civilization might lack the technology to breach the surface, condemning them to ignorance of the universe above. Do we intervene? Contact could trigger cultural collapse or provoke panic. Conversely, ignoring them might condemn a thinking species to eternal isolation. It's the prime directive dilemma from Star Trek, but with no Starfleet rules to guide us. Our very presence, even as silent observers, could disrupt ecosystems in ways we can't predict. And what if the life we find isn't just microbial? Rogue planets might host organisms so alien we don't even recognize them as life. Their biochemistry could rely on silicon instead of carbon, or ammonia instead of water. If we mistake a living entity for a geological formation, our experiments could inadvertently kill it. The history of Earth is littered with tragedies where humans dismissed other life forms as unimportant only to realize too late their ecological significance. On a rogue planet, with no second chances, that arrogance could erase an entire branch of the tree of life before we comprehend its value. The darkest scenario. Triggering a galactic-scale disaster. Some rogue planets might be delicately balanced, their internal oceans kept liquid by precise geothermal or tidal forces. Drilling into them could destabilize that equilibrium, causing the ocean to freeze solid or evaporate into space. If life exists there, our meddling could snuff it out in an instant. Worse, if rogue planets act as galactic gene-swapping hubs ferrying life between stars, our interference might disrupt a billion-year-old distribution network we didn't even know existed. Yet doing nothing carries its own risks. If rogue planets are the galaxy's arcs, preserving life in frozen stasis, then ignoring them might mean missing our only chance to understand life's universal principles. Their ecosystems could hold cures for diseases, clues to evolution's origins, or even warnings about existential threats. The choice isn't just about ethics, it's about survival. One day, a rogue planet might save us, but only if we haven't already destroyed what makes it special. Rogue planets could be the universe's ultimate time capsules, frozen relics, preserving conditions unchanged since the dawn of creation. Unlike planets bound to stars, where solar radiation and gravitational forces continually reshape surfaces and atmospheres, these nomadic worlds exist in near-perfect isolation. Drifting through the void for billions of years, shielded from stellar winds and cosmic collisions, they might hold pristine samples of the early cosmos, untouched by the chaotic evolution that transformed their star-bound counterparts. Imagine cracking open a planetary vault and finding the chemical fingerprints of the galaxy's infancy still locked inside. Take the building blocks of life, for instance. Earth's oldest rocks, dating back over 4 billion years, have been recycled by tectonic activity, their secrets scrambled by erosion and volcanism. But a rogue planet's icy crust could trap organic molecules from its formation era like amber preserving prehistoric insects, hydrocarbons, amino acids, even fragments of ancient RNA. These could linger in deep freeze stasis, offering a snapshot of the raw ingredients that once seeded life elsewhere. If life arose independently on a rogue planet, its biochemistry might reflect an alternate evolutionary path, one unaltered by the sterilizing radiation of a star. We could be looking at a fossil record not of bones, but of primordial chemistries, frozen in time. Then there's planetary formation itself. Astronomers still debate how gas giants like Jupiter coalesced so quickly in the early solar system. Rogue planets ejected in their youth could be time machines, their cores and atmospheres preserving the original ratios of hydrogen, helium, and heavier elements from their birth clouds. By studying their composition, we might uncover whether they formed like traditional planets accreting material from a protoplanetary disk, or if some collapsed directly from interstellar gas, blurring the line between planet and failed star. Each rogue world is a puzzle piece, locking in clues about the violent processes that sculpted the first generations of planets, but the most tantalizing possibility. These worlds could carry whispers of long-dead star systems. When a rogue planet is ejected, it doesn't just leave its star behind, it carries fragments of its birthplace in its chemistry. Trace metals in its atmosphere or isotopes in its ice might betray the unique signature of its original solar neighborhood, a cosmic DNA tracing back to a stellar parent long since gone supernova or faded into a white dwarf. In this way, rogue planets become celestial archivists, holding records of systems that vanished before Earth even formed. Yet accessing these secrets won't be easy. The same icy shields that preserve rogue planets also lock their treasures away. Future missions might need nuclear-powered drills to penetrate miles of frozen crust, or AI-guided probes capable of navigating lightless, high-pressure oceans. But the payoff could redefine astrobiology. If we find life or its precursors on a rogue planet, it wouldn't just hint at life's resilience. It would suggest that the universe's recipe for life isn't rare or fragile, but robust, adaptable, and perhaps as old as time itself. These drifting worlds aren't just curiosities. They're pages from a cosmic manuscript waiting to be read. Rogue planets shatter every assumption we've ever made about where life can exist. These cosmic nomads, once dismissed as frozen wastelands, now stand as some of the most promising frontiers in the search for extraterrestrial life, not despite their darkness, but because of it. Their very isolation could be their greatest strength, shielded from stellar radiation, untroubled by solar flares or wandering asteroids. Their subsurface oceans might have incubated life for billions of uninterrupted years, evolving in ways we can scarcely imagine. The galaxy's loneliest worlds could be its most fertile. Think of what each discovery would mean. Finding even microbial life on a rogue planet would prove that life doesn't need a star's warmth, just liquid water, energy, and time. That simple revelation would explode the boundaries of the habitable zone, turning the entire galaxy into a potential cradle for life. But the implications run deeper. If life thrives in these hidden oceans, it suggests that the universe isn't just hospitable to life, it's saturated with it, lurking in the last places we thought to look. Rogue planets could be the silent couriers of biology, ferrying life between the stars like seeds on a cosmic wind. Yet for all their promise, these worlds also humble us. They force us to confront the fragility of our own existence. Earth's biosphere clings to a razor-thin layer of atmosphere, dependent on the steady glow of a single star. Rogue planets, by contrast, endure without any of that. They are the universe's ultimate survivors, carrying the potential for life through eons of darkness. If they teach us anything, it's that life is far more resilient and far stranger than we ever dreamed. So as we gaze at the night sky, let's not just look for the familiar, the stars, the planets, the comfortable glow of solar systems like our own. Let's train our eyes on the emptiness between them, where unseen worlds drift in silence. The next great discovery in astrobiology might not come from a distant exoplanet orbiting a sun, but from a rogue planet passing unseen through our own cosmic neighborhood. The question isn't just whether life exists out there, it's how many of these wandering worlds are carrying it right now, right past us, in the dark. And if that's true, what does that say about our place in the story of the universe?